Distinguished ladies and gentlemen, let me welcome you to the webinar on the practice and principles of climate change adaptation and resilience for engineers. And today's presentation will be handled by a prominent engineer, very senior in the profession and very passionate about the engineering profession, and very passionate in making sure that engineers deliver disaster-resilient infrastructure globally. There is no other person than David Lapp, who is from Engineers Canada. He has been associated with the World Federation of Engineering Organizations for more than 20 years. And he is still very much strong and very generous to share with us his personal experience and insight on this very important subject matter. And this also reminds me of the fact that the WFEO website has a lot of information which our members really do not, take time to go through while it is there for them. So I want to use this opportunity to please remind our members, all the national member institutions, to make sure that, first of all, in all our national member institutions website, we should have an easy link to the WFEO website, so that if you are a national member organization or international member organization of the World Federation of Engineering Organizations, once you open the website, your own website, there should be a link to WFEO. And under the link, we have a lot of stuff, especially when you go to who we are or what we do. Under what we do, you see a lot of, documents for your own use, for your own practice. And I want to urge, members to please take their own time to go through these documents and also share these documents with their members wherever they are. And some of these documents are
Oh.
Sorry, I don't know. I think I was lost a little, I don't know. So we have, a couple of documents in this in this website for all of you to get accustomed to. So please, I urge all our members, national and international members, associates and affiliates, to please be frequenting the website for a lot of information. Another thing I also want to urge all of you is that we need to have some feedback, loop from all of you. While we are trying to serve, okay, I'm glad the IT officer, Ivan, has opened the website. You can see under this, what we do, there are a lot of links to various items. So as much as we are trying to satisfy the membership of WFEO, we also need like a feedback as to your opinion on the way we do things and what we are sharing with you, or what we ought to be sharing with you. And if there are some documents also you would want the global engineering audience to know about, please, we need such documents, so that when we go through it and it meets our standard, we also post it in, on the website, so that you share all this, stuff and information with the global engineering community. So the relationship between the WFEO Secretariat and the membership is supposed to be a two-way relationship. We get from you and you get from us, and we become like a hub whereby, you know, if you have things you want to share with the global engineering community, you bring it here, we upload it, then, you know, other people will get to know about it. And if you have opinion about or against the way the WFEO is being run, or some information being disseminated, please, we need such feedback so that we can make our work much better for all of us. And before I hand over to him, let me also use this opportunity to remind all of you that the Global Engineering Congress is, you know, is coming up in October this year in Shanghai, Shanghai, China. And it promises to be a very big event, and a lot of information sharing and networking, you know, will take place during that Global Engineering Congress. And we are going to use that opportunity also to have the General Assembly of the WFEO, where we are going to elect our next core of officers who will be leading the federation. I'm glad the Secretariat is sharing the web page of the the Global Engineering Congress. Just 3 weeks ago, I was in Shanghai, China, to see for myself with the executive director the proposed site for the Congress. And honestly, we are very pleased with what we have seen. Our colleagues, the China Association of Science and Science and Technology, are doing a lot to make sure that we have a very, very interesting and robust conference where you will meet a lot of leaders in the engineering profession, leaders in the political space, also global leaders in the political space. So I assure all of you that you are going to really enjoy and benefit a lot, you know, if you participate in the forthcoming Global Engineering Congress. So with this, I want to invite my colleague Ivan to make a proper introduction of the guest speaker who will run us through this code of practice. It is there actually in the website, but it is sweeter when you hear it from the authors of the document. So Ivan, please, I want you to give appropriate introduction of Professor David Lapp.
Yeah.
Thank you very much.
Thank you, President Shehu. So to briefly introduce David Lapp, he is a climate resilience and capacity development expert with over 40 years of professional practice. He has been involved in WFEO since 2007. He was the secretary of the Committee on Engineering and the Environment that was chaired by Darrel Danyluk and hosted by Engineers Canada for 8 years, until December 2015. During this period, the model code of practice he will present today was created and adopted by WFEO. And you can see his profile in more detail in the click you will find now in the chat box. So,
okay.
Yeah. So you may also be interested in the free online course called Sustainability in Practice, which opened 1 week ago and ends on 25 June. David Lapp is one of the instructors in this free online course. So you will find more information about this course in the link now that I share on the chat box. Thank you very much. And David?
Okay, thank you very much. So before I call on David Lapp, I just want to mention that we intend to listen to David Lapp for about an hour or maybe a little over an hour. Then there will be interactive session whereby the participants of this webinar will contribute or ask questions, you understand, so that whatever is being said during the webinar session, you take note of whatever you know you want to respond or raise question on. Then after he finishes, then we open the floor for the comments and questions, and then afterwards we close the webinar. So we are going to listen to him for about an hour or a little more. Then we open the floor for general discussion. So David Lapp, the floor is yours. Thank you. I'm not hearing you. Your microphone is off. David, your mic is off.
My apologies. Okay. Can you hear me now?
Yeah, yeah.
Yeah. I just wanted to say that Ivan is going to help me with this presentation by clicking through the slides when I ask him to do so. I'm a little technologically challenged in that area, so trying to do everything, including the presentation and so forth. So bear with that a little bit. I'll be just asking Ivan to help me out on that. Just another note just before I start this presentation on that course, Sustainability in Practice. It is a free course that can be audited, or you can pay a fee to take the final exam, and then you get a certificate as well. And that is a self-paced course, so it is open now. You can take the course at your own pace. You just need to finish it by the end of June. So. And we've had more than 11,000 people take this course around the world, and we're hoping to increase that number even more this time. So, and it's actually around another code of practice on sustainable development and environmental stewardship, which a version of which is also on the WFEO website. But enough about that one, because we'll do that another day, maybe a presentation on that. But for today, I'm going to present about the code of practice around the principles of climate adaptation, and in the future, as it's undergoing a revision right now, adding the notion of resilience. So can we go to the presentation there, Ivan? Okay, so next slide. Once we get it up on the screen. Okay, thank you. So just to give you a bit of an outline of what I'm going to cover today, start off with some introductory remarks around the notion of our changing climate, and a bit of an engineering 101, just to relate it back to the notion of loadings on infrastructure and that sort of thing. Then I'll talk a little bit about the code, the development of the code, its status at the moment, and authority and application, because we're talking about a model code. So this is a code that is a voluntary code. It's not mandatory, but it can be made mandatory by national and international members if they so wish. I'll then go through the existing principles. There's 9 of them, and I will go through them to some level of depth in the time I have available, but I certainly encourage folks to upload this document and read through it. There's a very rich documentary in there, a description of things. It gets into a level of detail that we can't possibly cover here. But I think it can give you some good guidance on how to think about climate and how to adopt these principles. We're also, the document is undergoing a revision now because it was published 10 years ago. And since then, we've had, quite a bit of evolution in the notion around climate change and resilience. So back in that day, resilience was really not a concept that was well defined or understood, and we feel that this is an important piece that needs to be added to the document, plus some other methodologies that are being used now that are becoming more common in practice, which refer to nature-based solutions. I will then have a few closing remarks, and then we'll get on with the questions and discussions. As Mustafa said, it should be about 45 minutes to an hour that I'll be talking, and then we'll go into the number 6 after. So next slide. So one of the things that I wanted to get us back to Engineering 101, and the basis for this is the fact that our climate is changing. We've got changing precipitation, changing temperature. If you can just hold it there, Ivan, please. And our climate in the past has been what we would call stationary climate, where it was fairly within a range of values of climate that we could use for design and so forth. And because of our changing climate, that is no longer the case. We're seeing these changes, shifts in the means, more extremes, more frequency of extreme events, that sort of thing. So we consider this now to be a non-stationary climate, being non-stationary, which means that we need to adjust our practice to account for the fact that our climate is changing, and we don't know so much how much and how soon, but we do know it's changing, and the climate science is irrefutable in terms of that. We typically refer to it as changing climate rather than climate change, because it's certainly absolutely true that the climate is changing. So given that that's the scenario where we talk about the notion of non-stationarity of climate, just wanted to review briefly the notion of how do small changes in climate potentially lead to failure of infrastructure assets. So here you see in this diagram, you typically have a capacity for your infrastructure that exceeds the load, and then you add a next click. You add a safety factor. As everybody knows, we typically, because to handle the properties of materials and other uncertainties, we always add a safety factor onto that, but that safety factor does not include a change in the climate. Next click. Then as the infrastructure gets used over time, its capacity reduces as it ages and so forth. And next slide, next click. It reduces down to a certain level where and then what you see on the load side is, the original load that was on that infrastructure can change over time as well because of things like the change of use. It may be used more intensively, more time being used, et cetera, that sort of thing. And so you see now that the load is getting, it's when you have a climate event, which is an extreme event, then the load exceeds capacity, and what you see there, next click, is a potential failure condition. So the trigger for the failure is the climate event. And what we need to understand is what the nature of these climate events is, their frequency, their magnitude, and that sort of thing, because they can trigger a failure. And we've seen that many times in the world where we see the loads, additional loads from the climate, inducing large scale failures of infrastructures. Next slide. So of course, because of the fact the climate is changing, we're not sure exactly how much and how fast, but we do know that it's shifting. And if you see the line there, there's an infrastructure threshold that could be a design under which the below that threshold, the structure is safe, it's sound, it won't fail. Then next slide, next click. So you see that the probability, that's a probability distribution of that climate parameter, is there's a small area there of potential failure condition, where if the climate variable increases over that level, then you could see a failure condition, but it's a fairly small chance. And then, that's what you design for, as a small chance. Then the next click. And you see the as the climate is changing, there's a shift in the mean. It increases. Next click. And what you see is then the probability of failure now of exceeding that threshold is increased because even the mean of that climate variable has shifted to the right. Next click. So you can see there's a larger area for potential failure condition. Next one. The other thing that happens with climate is we're seeing, more variability in the climate. So you may see some of the extreme values being occurring more frequently. And so that combined with a shift in the mean, next click, and you see that area increases even more. So that infrastructure threshold that you've used to design that infrastructure is no longer adequate to handle, perhaps the probability of failure that's contained in that shaded area. So what do you have to do about that? Well, you have to take that into account. And that means things like shifting that infrastructure threshold to the right so that you can actually reduce the probability of failure. So this means adjusting your design values. And so that's the kind of the logic behind why we need to consider climate change over time. Next slide. So it comes down to the fact that we don't know there's a lot of uncertainty with respect to the climate, and therefore we have to start to undertake things like assessing the probability of change of that climate. So you have the probability of occurrence on the bottom scale there, and then you have the consequence of that failure. And this is what we refer to as climate risk assessment, and you have a risk assessment matrix. So just to click on the first one. So, say in an existing condition, you have a flood that is a low probability of occurrence, but a high consequence. And then with climate change, it shifts to the right because it's now happening more frequently. So it shifts from perhaps a low to medium risk into a high risk area. And through adaptation, climate adaptation, next one, you can reduce the risk to a manageable level. Even though that flood is happening more frequently, through adaptation measures, you can reduce its risk, i.e. the consequence, down to a level that's manageable and tolerable by the owner of the infrastructure. So the key here for engineers is to propose adaptation measures that will reduce the risk from climate events to make it to an acceptable level, reduce the consequence of the impact. Next one. So I wanted just to step back for one moment just to say, here we're talking about climate adaptation. Okay, so we're adapting to manage the impacts of climate. There's another whole area of work which people would know about called climate mitigation, which is the notion of trying to reduce the rate of change of climate, perhaps stop it, perhaps. That's perhaps a little ambitious, but at least to reduce its rate of change so that, and this is the whole notion around reducing greenhouse gases and those sorts of strategies. We don't deal with that here in this guideline. That is a whole separate area. And so what we're talking about here is, given that we've got this changing climate, how do we adapt our infrastructure to handle it? Next one. So here's a kind of a way of relating this back to when should one intervene when you want to, I guess, reduce the impacts of climate. And this is some work that was done probably 15 years ago or so, looking at the functionality of say a system or an infrastructure and the service life. So one of the principles that's really key here is we're looking to maintain a functionality over the service life of an infrastructure, which can be anywhere from 25 to 100 years. And during that time, the climate is going to change. Again, how much and how when is still a subject of a lot of work that's being done by scientists, but nevertheless, it is going to change, and there are probabilities of changing climate parameters. So let's just next click. So say you have what they call an extreme event, that event that trips the failure of that infrastructure. And so at a certain point in the service life of the infrastructure. Next. And if you do nothing, and you just let it happen, then you're going to see a functionality that's reduced to either very little or zero, especially if it's destroyed, the infrastructure, and it's going to cost you an awful lot of money to recover that functionality that that infrastructure was providing, and it'll also take a long period of time. Next slide, next click. Now, if you take an adaptation measure in advance of that event, so anticipating that this event could happen, and then what you take that sort of in advance, the next click, then what you'll see is the functionality will be reduced perhaps to some extent. It might be out of service for a while, but then with the proper design and recovery measures, you can have a quicker return to a functionality that costs much less money. And the next one, and then some of them, there's sort of middle grounds, of course, where you don't do the intervention, but you put a lot of effort into the recovery. So, but again, you can see that if you intervene earlier and anticipate what could happen here, then the recovery and the cost is much less. And there's a reference here at the bottom, just click that. If anybody wants to look into this work, it's a really good way of looking at things. I think relating the whole notion of climate impact and design and recovery into sort of one sort of story there. So I'd recommend folks to actually look at that reference and learn from it. Next one. So just moving on to the Code of Practice. As mentioned, it was approved at the WFEO General Assembly in December of 2015. So it's been in existence for about 10 years. It is on the WFEO website, and that is the link there that you can directly access it. But as we mentioned before, it's buried. It's not clear. There's not even evidence that it exists. And that's one reason why we're doing these webinars, is to increase the awareness of this document, because we feel it will contribute significantly to engineering practice in this area. It's a voluntary code, so WFEO doesn't have any regulatory or legal authority, so we feel this is like kind of best practice, and it's focusing on the professional and ethical aspects, which are common to all engineers. Doesn't matter what discipline, all disciplines pretty well get affected one way or another by climate. And it may not be obvious for some disciplines, but there are a lot of linkages. For example, mechanical and electrical engineers are affected because they may need to adjust their designs to handle, for example, increased heat, meaning a bigger HVAC system, just as an example. This document is kind of like, as we say, a model code, and at Engineers Canada, where I worked for 23 years, we actually used this document to develop a mirror document for Canada called Principles of Climate Adaptation, and it was later extended to include mitigation, known as a public guideline at the national level. So again, it's a voluntary guideline, but it's very much a mirror of what is in this document, and this is one example of how a national member or an international member could adopt this document to become their own, either as is or whatever. And as mentioned, we're updating it right now through the WFEO Working Group on Climate Change. So we're hoping that we can get a draft for review and over the summer, and then hopefully an approval at the General Assembly in October of this year. Next one. So the purpose really of this and the authority is to provide guidance and to inform engineers, defining a scope of professional practice relating climate and infrastructure, or changing climate and infrastructure. As mentioned before, it's very advisory. It's one of the things in this business, and in fact engineering in general, is you have to exercise your engineering judgment. It's not just a number, it's the judgment of applying that number. And climate is yet another factor that one has to consider. And so helping, where do I start? How do I actually incorporate climate into my thinking and my decision making? And this is what this document helps to do. It's also to, gives instruction on balancing, as they say, competing interests. So you've got your client who wants to build something as cheaply as possible and as quickly as possible, may not be thinking about the service or life cycle of that infrastructure, which includes the maintenance. And so your responsibility as an engineer is to go through a process to explain to your client or your owner of the infrastructure the potential impacts of the climate and the measures that are needed to improve its resilience to climate impacts. All that being said, as we always say, is that engineers often aren't the final decision maker. Sometimes they are, and if they are, this is great because you can really think about bringing in climate. But a lot of times it's an owner decision or a client decision, and what you're trying to do is to help them make the best informed decision and discharge your responsibility as an engineer to advise them on climate impacts and what to do about them for their infrastructure. Next one. Ivan, can you go to the next one? Hopefully. Oh, there we are. Okay. So the language that's used in the Code of Practice is there's 3 terms to be aware of. A lot of statements say should. Okay, so one should do this or should do that. And what that really means is it's a strongly preferred recommendation based on the review of the practice. We think this is the way to go forward. But, if you decide not to do it, nobody's going to penalize you or enforce on you. So we refer to that as non-binding. Okay, but it's highly recommended. So to follow that. Some documents, not so much this one, but other documents use the word shall or must. And that is as a requirement. It may be a legal requirement, a financial requirement, compliance. And there's a potential for sanction if it's not followed. So particularly in Canada, we have a regulatory environment for engineering that strongly is associated with those first 2 words, should and shall. Engineers Canada, we can only do should. Our regulatory bodies that we serve can use shall or must because they're the ones that regulate engineering in Canada at a provincial level. The last word is may, and that's really presenting one of several options. That's at the discretion of the engineer, but it's kind of giving you some of the options. It depends on the situation that you're in and what infrastructure you're designing, where you are, a number of other factors that are really just, again, to help you think about it and with some options to begin with. Next one. So as I mentioned earlier, it's, WFEO is not a legal authority. So we don't have any, there's no requirement that WFEO can enforce. Ours is persuasion and coercion, whatever, bribing, probably not bribing, but in any case, we're there to be a resource, to provide advice, to provide guidance. And it's, this is one of a couple of documents that exist of this nature at WFEO. And Engineers Canada, we have quite a few more that get into the practice, but more on the professional and ethical sides. And really what this code is, this model code is, it's been mutually agreed by all the members, national and international members of WFEO as a good representation that would cover this particular issue. And as mentioned, national members, we really try to encourage national members to receive this document. And basically, we've done all the work and all the thinking behind it. And so national members could adopt this document as it is and basically just put their own logo on it or new front page if they want, or they can take the document, modify it to suit their local situations, and then publish it. But a lot of the work and thinking has been done with this document. So it's probably in a lot of those kinds of cases might be 75 or 80% there. So the incremental work that's needed is much less than if you started from scratch. And that's one of the services that WFEO provides. And but one of the things that with these kinds of documents too is that if for example you have a contract which says you must follow these principles in doing the work for this infrastructure, then it can become a legal requirement because then you're into a contract which makes reference to that. And that's typically done for codes and standards where, for example, you may have a building code that's not a mandatory code, but because the contract requests compliance with that code, it then becomes a legal requirement. So just to give you an example of where that can happen. Next one. So the way that the document is structured is, again, we have 9 principles, basically a description that starts, then an amplification, so a little bit more of an explanation, and then implementing actions. So this is not just sort of a theoretical, oh yeah, this is a nice thing to do, where it actually provides guidance that helps you to implement and follow those principles. And it gives examples of actions that can be taken to address these concerns. And of course, it's not limiting. These are just a number of actions, but part of your engineering work is to think up the solutions and implement them. And what we're saying here is you must think about climate as you're thinking about these solutions and incorporate it, where appropriate, and so forth. So that's really the notion here. It's giving you that framework under which to think about this issue in the context of the work that you're doing. Next one. So here on a one summary page, and I'll go through this in a little more detail than this, but just to say there's 9 principles, and we're looking at doing a couple more as part of the updating. But the idea here, the goal of executing these principles is to ensure that engineers have considered the implications of climate change in their practice, and and equally important that they create a clear record of their considerations. So it's not just in your head. You got to write it down, document it, because that helps you to justify to your clients that this is why we need to do this. So documentation is an overriding issue on all of these things, that you need to be in a position to document. And of course, everybody's got their own ways and standards of documenting, but the point is that you need to include the climate considerations that you've made as you're doing your work in design, construction, or the operation. So I'll go through these to some level, but again, it's impossible in a webinar like this. I could actually, obviously, there's enough there to have a whole full course on this. Maybe someday we will if we get some resources to do so, but for now, we have the document, and I will briefly go through each of these to a certain level and encourage you to go to the document and read further, because there's just no way I can present every aspect of each of these. So next slide. So we'll start off with, integrating climate adaptation in practice. That seems like really obvious, but in fact, there's a lot of engineers out there that don't necessarily do that and haven't done. They just go ahead and design as if, everything's going to more or less stay the same. They don't account for it, and then there's problems down the road. I can tell you an example that I just came across about a week ago in Toronto, where they're redesigning an expressway in Toronto, and there was an engineer who failed to take into account the stormwater changes in stormwater, which when they discovered this error, it cost Toronto about 8 or 9 months of schedule to account, to do the design and to adjust the construction and so forth. And that company, that employ that engineer is actually being sued by the city of Toronto. So there can be some serious consequences if you don't consider climate in your practice. And that's just one example. But part of this, of course, is that you're going to need to understand the climate science, the science behind it, like to understand what's happening in your local area where your infrastructure is going to be constructed and operated. And so you got to understand that what is the current baseline of the climate, the variability, what's it projected to be, so you need to get not become an expert, a climate expert, because we have people that do that, but enough to be able to ask the right questions and to calibrate the answers to help you inform your engineering judgment. And this includes all elements, in the design, the construction, the operation, the maintenance, planning, and even in procurement. You need to think about, hey, if I'm on the client side and I'm an engineer writing a statement of work for an infrastructure, I need to think about what do I have to specify in terms of climate consideration as part of that, say, a tender document for that infrastructure. Next one. So some actions to implement. For example, what are the climate parameters that are going to potentially have an impact, and how are they going to change over the where the project's located, and the life cycle. Is it 25 years? Is it 100 years? Whatever. And you need to assess with yourself, with others, not just yourself, but with your team, what elements of that infrastructure are going to be impacted by these climate events. What are the weakest links if it's an existing infrastructure, or even the design? Maybe there's an aspect of the design that is it's the minimum, and maybe the minimum's not good enough, to deal with future climate. And then you have, of course, to figure out, okay, if I have weakness here, how am I going to beef up that infrastructure? Is it going to be through the design or through better operation and maintenance? That's those sorts of considerations. And part of this, as the second to last point there, maintaining a record. Let's make sure that you document the discussions you've had, the decisions that have been made, so that again, that covers your responsibilities as an engineer. And that's it's engineering judgment. And I come back to that because engineering is about judgment. It's not about just using a number and plugging it into a formula. Even a scientific formula that produces a number still has to be assessed. Is that the appropriate number to use for a design, or do I need to use a different number because of the situation? And climate being one of the big factors, well, maybe this is not good enough for covering the next 50 years. And that's judgment. And you'd have to bring that into account. And you need to document it so that your assumptions are documented. Next one. So a huge resource for engineers, of course, is codes and standards. In Canada, we have quite a well-developed code and standard system. We have a national building code, for example. We have codes at the provincial level as well. We have bridge design codes. We have lots of codes and standards. These are minimums. These assure safety, but they do not assure performance of the infrastructure, the durability of the infrastructure, the ability to recover. And also, codes and standards are often behind what the science is. It takes several years to adjust those codes and standards. So they certainly are a minimum, and you need to do those because those are within a legal framework often. If you don't have codes and standards in your country, or because that happens, or some don't exist for certain infrastructures or situations, then I would say go to some international standards like the ISO. Has a series 14090 that talks about climate adaptation and infrastructure. And I would recommend that, if in the absence of having things in your own country, you go to those kinds of standards. And there's quite a few of them out there, and they're international. The only thing about them is they are, to a certain extent, general, and they don't necessarily fully apply or to your local situation, but they're better than nothing. And again, you use engineering judgment when you are applying those standards. Next one. So again, you're getting, sorry for some of the typos here. I had sent a revised presentation, but it didn't quite get into the queue here for today. But anyways, that being said, you want to obviously use the most current codes that exist, so not old ones. The most recent ones, codes are evolving to include climate change. Certainly in Canada, we've got quite a bit of that going on. Hopefully in other countries, I would encourage other countries to look at their codes and standards and to start updating them based on future projections of climate, for example. And then again, you use those as the baseline. So again, adjust for your situation. If you think a climate parameter is going to be exceeded because of extreme weather or that sort of thing, then you may want to take that into account in your design rather than the code value. Next one. Oh, one other point on the codes too is that you want to if you deviate from a code and you use perhaps say a higher number, you need to document that as well and the rationale for it. So again, documenting your judgment, and which leads to the next principle, which is the looking at the impact of the current climate. So you have a history of climate events, say it's an existing infrastructure. You can use that to sort of determine like how will this infrastructure respond to the current climate, and then what would that be like if the climate has changed and some of those values are greater, extreme values. This is very helpful. And again, the documentation of your engineering judgment that included in codes and standards, but also just the climate design parameters that you're using, and what ones did you use and why, and again putting that in a document and the rationale for that. And part of that is engaging with outside experts, other people that they're other engineers, like particular engineers, say a structural engineer perhaps, or a hydrologist or coastal person, these sorts of other practitioners. So you don't do this all by yourself. You do it with and as part of a multidisciplinary team. Next one. So again, the checklist of climate parameters. Consider, what climate information you're going to use. So again, like, am I using local climate data? Am I using climate data from 50 miles away? Or am I using a national database? Again, those are all sources that you need to look into to see which is most appropriate and current and representative. And that takes the advice also of a climate scientist to say, is it scientifically defensible, that data to use? Again, the whole notion of documentation. Make sure that you document what kind of a review that was done, and what adjustments were made, that sort of thing. And there should be an engineer that's responsible to prepare that, or at least review it and sign off on it. And then the engineer has discharged their professional responsibilities for considering climate change. Because one of the things you don't want to have said is, did you consider climate change in your design? And if you have to say yes, and if I'll prove it, well, that's where the documentation comes in. And there are cases where no, the climate was not considered. And then one might have, if there's a failure or whatever, then and determine what the cause was, then it gets to be very, very difficult, and can be very difficult for the engineer versus the owner in that situation. Next one. So climate, of course, is key to all this. As I mentioned, you've got these shifts in mean and variance, and they're going to change going forward. And how fast, how much, that requires the expertise of a climate scientist or a climate specialist. So you almost always need to work with one unless you happen to have that expertise yourself, but most engineers don't. They have some knowledge maybe, but that's where you bring in a specialist like that to tell you, okay, what are the what are the future values and how confident are you about those values and what are they based on, you know, that sort of thing. And so you want to understand what are the uncertainties and the sensitivities, you know, what if the value was twice what you've given us, you know, what would that mean? Is that possible? Asking those kinds of questions. And really the idea is that, you know, projecting climate in the future requires modeling. There's a lot of models out there. Many of you would have heard of climate modeling. And the best practice there is to use a selection of models, like more than one, ones that are more scientifically defensible and applicable to the area or that you're working in. So that's an area in itself to try to understand, you know, what is available and what is scientifically as defensible as possible. Next one. So again, you want to understand what is the climate in which this infrastructure is going to be operating now and over its life cycle. And one of the things you want to really look at is the frequency and intensity of extreme events, extreme values of these, because that's where that can trip, you know, as we saw in the very beginning, that, you know, that climate event can trip a failure. Even though it may be sound without that climate event happening, it's still safe or it's not going to fail. But that climate event is what triggers the failure. And so it's really important to understand what is the climate event, how frequently is it going to happen over the life cycle. And one of the things you see, for example, in that threshold that you saw at the beginning, if you keep that threshold, the chances of that happening are more frequent. So, for example, you could have an event that causes a failure once in, say, 50 years, but because of climate change, it could happen 5 or 6 times. Do you want to have to repair and fix this infrastructure 5 or 6 times in the next 50 years? Or, you know, do you want to shift the design value so that, again, you know, it's down to, you know, one or once maybe, and then that's again a maybe, right? So it's really important to understand how frequently certain values are going to be exceeded, because that could change the strategy of how you design, operate, and maintain that infrastructure. And that, as I mentioned here, involves working closely with climate scientists. Next one. You know, there's lots of the data sources. You know, there's measured data, you know, at meteorological stations. So that's real data that's been collected at a station. We always recommend, hey, you know, when you got an infrastructure, set up a weather station at the infrastructure and start collecting data, so that when that infrastructure needs to be replaced, you will have, you know, 40 or 50 years of data that you can use to inform your next design or your rehabilitation, as an example. And, you know, you also need to, again, be aware of the scientific methods and so forth that are used to derive these data and what are good and what are not so good, so you can calibrate your engineering judgment. Next one. So working on this kind of thing related to infrastructure, not only do you work with climate scientists, but you work with other practitioners, and depending again on your role as an engineer. So and the infrastructure. So, for example, you know, if it's a coastal infrastructure, you may work with obviously coastal like hydrologists, for example. If it's in the mountains, you may want to get a landslide specialist working or geologist working with you. So some of the natural scientists may help you to advise on, you know, impacts on the natural system that in turn could create difficulties for your infrastructure, e.g., a landslide. You know, if a landslide increases because of heavy rains, you need to account for that in your infrastructure somehow, then, you know, you want to know that that's a possibility, right? So you're not going to necessarily have that expertise, but there's people that have that, right? So there's a composition of a team. It's a team effort. and it's multidisciplinary and it's multi-stakeholder because it's the owner, it's the engineer, it's the natural scientists and so forth that are, and then also the operators and maintainers of infrastructure are important to involve. So the next slide talks a little bit about some of the expertise that you want to have in your team. So next one. So these are, I'm not going to go through these in detail, but just to say that this slide and the next slide, just go to the next slide too, again, is these are skills and experience that you want to have on your team. So when you're forming your project team, you may not have all of them because it depends on the situation. And sometimes, people have multiple areas of expertise, but there's no doubt that you cannot do this on your own as an engineer. You need other people to advise you, to consult with, because they have expertise that you don't. Next one. Again, so key is communication. Engineers are not known as the best communicators, but we try. We think we communicate well. Sometimes yes, sometimes no. But this, in order to get buy-in for adapting infrastructure, you need to communicate effectively with your client or your owner to make them understand, that they need to bring this into account. It is going to cost you more money, probably. But in the long term, you will have a structure that lasts for that period of time, gives good service and that sort of thing. That's sometimes hard to envisage, like and I liken it to an asset a field called asset management. Life cycle of an infrastructure is a very key element of asset management, and if you can't get your owner to recognize that an infrastructure that they own is going to be there for 50 or 100 years life cycle, it's going to be very hard to sell them on climate change, because that's the notion. They're very closely tied together. You're trying to make sure that this infrastructure lasts over that period of time. So part of that is, of course, defining the problem and then proposing the solutions and the costs, the benefits, and so on, the risk reduction thing that we talked about at the beginning. These are all things that need to be bundled together and communicated to ensure effective decision making. And there's also an element of dealing with the public about an infrastructure and to inform the public, what are the potential impacts of the infrastructure? What if it doesn't work for a period of time, doesn't provide power, for example? What does that mean to the general public? That sort of thing. Next one. Again, I mentioned the service life. I won't go through this in much more detail than I already have. But again, some of these decisions also are not just technical ones. They're also have economic and social impacts. So, what if an infrastructure isn't available for, a month because it's been destroyed? That could be really important to a community. So you may want to take measures that either resist more or recover the infrastructure much faster so that it's not out of service for the people. And you need to understand those consequences that go beyond just physical damage and so forth. And one of the things, strategies that's very, very helpful is, you don't need to necessarily do everything up front. Maybe you can design it so that, partway through, you can make some adjustments. So a good example of that is heating and ventilation. You may put in a system that covers, a much hotter temperature 20 years from now, but you don't need to put in the equipment to provide that because it's not needed right now, but it could be later. And so the cost to make that change is much less than if you had to put in a whole new system to provide that service. So that's just an example. Next one. So I've mentioned at the beginning around risk and understanding the risk, and in my professional practice, I would have to say that understanding climate risk is an essential and first step before you even design a system. You need to understand the risk under which that infrastructure could be subjected to. And if you don't have that, then you're navigating in the dark because you don't have, you don't know what to prioritize and that sort of thing. So you need to develop a risk profile. And so I would say, as part of training of engineers, is become competent in the whole notion of risk assessment. It's a science that's been around for 30, 40 years. We've applied it now to the whole notion of climate risk. And I will just, the next slide, just put in a small plug for a project that we did at Engineers Canada to develop a protocol for this that analyzes the interactions between climate and the infrastructure components. It's called the PIVC protocol. And if you want to find out about it, it's the www.pievc.ca. And that website contains a number of products around this type of work and more than 100 reports that show the application for various infrastructures in Canada. So I'll just leave it at that, but it's pievc.ca. Check it out. Next page, next one. So just to show you that there's a structure to this protocol, a number of steps that are taken, the result being that you get a series of recommendations on how to deal with that risk. You can assess the economic and social consequences of that, of those, the options, how to adapt. That's all part of what the scope of this protocol is. Next one. Last principle that we have that exists is around legal liability. I've talked about this a little bit before, but again, there's contractual liabilities. There could be the legal system of a country may have certain penalties that an engineer may be subjected to if their practice is not competent or there's some ethical violations, that sort of thing. So again, knowing what the legal requirements are from the legal standpoint, but also a contractual standpoint, you should know what those are. What are the consequences? That will also dictate how you approach the climate consideration. And as I say, the way to deal with this is to document. So if I have one other word, I would say, besides say risk assessment, it would be documentation. Document your thinking. Make sure you're covering yourself and what the decisions that you made, because they are engineering judgment. It's not just a number. Next one. So we're getting into just a couple of quickies around what we're looking at to update this document. One is the notion of resiliency. This has become a principal objective now of infrastructure and, of course, in many other elements related to climate. And that's beyond adaptation. It's not just adapting the infrastructure, but the ability to recover. And so a climate resilient infrastructure, the definition we're planning to use, although we're going to add the word constructed in here as well. Infrastructure planned, designed, constructed, and operated to withstand climate impacts with ability to recover and provide service quickly after disruption. So you get a climate event, it knocks out the infrastructure, even though you may have designed it. It just is such an event. You can't make an infrastructure totally climate proof. It'd be too expensive. Anyways, the idea being that part of your planning is how do you recover that infrastructure? How do you repair it quickly to get it back into service? And that's a measure of the resilience of the infrastructure. So we're pretty confident that this will become another principle within the document. Next one is the notion of nature-based solutions. So this has become an increasingly important solution to infrastructures for certain situations, where you can use nature to help to minimize or reduce the impacts, particularly things like sea level rise. Using nature, like, for example, mangroves. You could, instead of cutting down the mangroves, you actually encourage them because they handle sea surges and sea level rise so that the coast is not damaged. And in some cases, that can be much more effective than putting up a great big seawall, which costs a lot of money and can be pretty ugly. So, but probably in the case of coastal structures, you would probably have a combination. Some areas may need a wall just because of the way the geography is or the situation, but there could be other areas where there's nature, and there's more benefits, of course, to nature solutions than just the solution around climate change. It has societal benefits as well. So, next slide. So just I guess to plug this a little bit, like how could that work, for natural infrastructure? Well, one of the areas that has, I think, great potential is in terms of flooding, reducing the impact of flooding, erosion and drought, water retention, for example. You can use that. You can use nature to actually, manage the water in a way that is far more effective than man-made structures. So again, this is something to include in the suite of solutions that one would put forward in dealing with issues like flooding. Next one. And then in urban centers, you have extreme heat. So that's a big health impact on people. So putting in tree canopies in urban areas will reduces the temperature impact on the pavement and on people that are outside, and provide shade and also have the societal benefits. So tree canopies are something, and there's a whole science around what are the best trees depending on where you are in the world, and that sort of thing. So there's a whole area of possibilities there. Next one. And this is getting to the stage where they're actually starting to create guidelines around it. So in Canada, this is one that's been published within the last year. And so there's enough of this kind of work going on that we can start to, one might say, document and standardize it a little bit, so that, again, it helps others to adapt to their situation. Next one. So I'm coming near the end. And I guess in closing, I would like to just say that climate consideration is now a central consideration for any engineer that's involved in infrastructure, because it has such an impact. And we need to make sure that our infrastructures are resilient for their life cycle, not just next week or next year, but 20 years from now, 50 years from now. So involves a combination of design, construction, and operation and maintenance measures to find that sweet spot between all those strategies for the most cost-effective solution. And it's so really what I'm saying is really we need to integrate this into our practice. This just becomes part of who we are and what we do. And we think about it consistently and one might say almost constantly to make sure that we're always taking that into account in the work that we're doing. Certainly we're seeing in Canada, and I would expect in other parts of the world, we've had so much damage, so many extreme events, and it's disheartening to have to reconstruct and start from scratch sometimes. And we as engineers, we can make a difference here in terms of reducing that occurrence and the expense and the cost through good measures, good practice in what we're doing. And that's being demanded more by governments and by infrastructure owners. So we're seeing that on the increase. Also, the insurance industry that insures infrastructure is also demanding this because they're paying out big money for this. So the demand is increasing, and we all need to, jump in and embrace this. Data is getting better, projections are getting better, but there's still a long way to go in some countries where meteorological data and records are incomplete or not available. We were involved in one project in Vietnam where we had to digitize weather records from 40, 50 years ago that were still on paper. So there's a whole exercise here that's that's needed and can be driven by engineers and others that need this data. So approach your weather services and that and say, look, we need to get a good data set that we can work with, so that we're not making, assumptions. We have some scientific basis for some of the numbers that we need to use. Next one. And there's a lot of tools out there. And there's almost too many tools at times, but this just gives you an example from one center in Canada called the Intact Center. They're involved with the insurance industry, and they have these various written resources to deal with different climate events, related events, and elements around climate that, it's not just the engineering, but it's also the financing of it, the legal areas like the capital markets you're seeing there. So there are things out there, and I encourage folks to seek out these resources, hopefully in your country, but if not, there's a lot of work being done in other countries. Canada, I would say, is right up there with respect to resources that they have available. So next one. So just sort of put together a final laundry list towards achieving climate resilient infrastructure. We need the climate risk and vulnerability assessment work needs to be done, which can be applied to new designs, but also retrofitting or rehabilitation. Also use that to inform codes and standards adjustments. If something seems to be riskier, then maybe we should adjust that infrastructure threshold number. And I think finally, I would just say capacity development. We all as engineers need to become more proficient in this. And so there needs to be courses and certifications that are, impart a body of knowledge to practicing engineers. But I'd also say engineering students should know about climate change, at least the basic science, when they graduate, so that they are aware of the importance of this particular factor. And that is different from country to country. In Canada, I've tried for 20 years to try and get climate change into undergraduate engineering curriculum. Haven't succeeded yet, but that doesn't mean I'm not going to still try. But it definitely, we need to get a higher level of understanding and competence among engineers. Next one. The whole notion of, it isn't just about design, but it's also the operation and maintenance of the infrastructure. So, the body of engineers gets involved in that. And it really, that extends the life, make sure that infrastructure is going to operate the way it should. You can't just do no maintenance on infrastructure. You've got to put something in place to handle all those weather events in good practice. And then there's a whole notion of the regulatory environment of the government. Engineers can be a voice in terms of developing policies, funding mechanisms, that sort of thing. So don't just, if you have time, not that you engineers have a lot of time a lot of times, but if you can get involved in helping to advocate for changes in these areas, because it's desperately needed. Again, we can't do this all by ourselves. We need these other groups to work with us to ensure that we can, do our job as best we can. Next one. So I just would say as a final statement that this code of practice that we've presented today is a consistent framework. It gives you guidance for a structured and fulsome consideration of climate in your practice as an engineer. I really believe that. And one of the measures of that is here we are 10 years later, and I would have to say, and I been involved with this field for nearly 25 years, that those principles remain the same. As I say, we're adding a couple, I might tweak a bit of the detail about how, but those guiding principles remain valid. And that's the sign of I think a document that stands the test of time. So that's why we're updating it. We're not starting over because what we've got is already pretty good and it still applies. So next one. And thank you for listening. So I Guess I went over a little bit, obviously, but
Thank you very much, David Lapp. Thank you so much. You have really, shared, a very insightful discussion with us, and I think this is just maybe the beginning of the beginning. And what I want to tell the audience is that, first of all, these slides will be shared with all of you. And I believe the secretary should maybe, put it on this chat box, or otherwise we can send it to all our national member institutions so that they can download for further reading. And the other thing I want to say is that these documents are there on the website of WFEO for all of you to be going through. And I also need to recognize the presence of some very important personalities in this webinar, especially the chairman of the Working Group on Climate Change, Davide Stronati, and Darrel Danyluk, who used to be the chair of Environment Committee of WFEO for many years. I'm glad he is, because this work actually started with him, years back. So Darrel, thank you very much for being part of this webinar, and Davide Stronati for organizing this webinar and making sure that it happens. I also observed that we have some executive council members who have joined us, Engineer Manuhwa, Nathaniel Matalanga, Jeng, are all the executive council members of WFEO. And of course, we have the president of FEO, Rafuli Butalazi. We have the chairman of the International Affairs Committee of the Nigerian Society of Engineers, Valerie Agberagba, and Sanzan Diara, also from Zimbabwe. And a lot of my friends also who have joined. I'm glad some engineers from Kano also have joined, too numerous to mention. So as we said earlier on, we are going to open the floor for some comments and questions. And then after that, we round up the discussion. I don't know whether maybe to open the floor for discussion, whether Darrel Danyluk or Davide Stronati and Manuhwa, if they have something to say, maybe I call on them first. Davide, yes?
Thank you, Mustafa, for the opportunity to open the debate. Well, first of all, thanks, David. As always, a really interesting and rich presentation. I just wanted to say, in my career, I've been working in consulting. Now I'm working in an asset owner organization. And we all know that climate resilience is a difficult concept to grasp, really to sell to board executives and so on, because it's all based on projections, statistics, and when money is tight, finance is tight, there must be some sort of scrutiny on how we spend our money. Nevertheless, there's a moral judgment, there's an ethical aspect for engineers to always design and work based on evidence. And there is evidence that the climate is changing. And there is evidence that providing resilience to our infrastructure pays a dividend. So this code of practice is extremely important because it gives a little bit of a blueprint of what we need to consider when we design, run, operate, maintain, plan infrastructure, wherever we are on this planet. So I just wanted to say that this is important stuff that is going to stay for the long term. I'm afraid we are going to be used to deal with a changing climate. Thank you, Mustafa.
Okay, thank you so much. Darrel, anything to say? Or
Yeah, so Yes, thank you for giving me the opportunity to speak. The evolution of the thought process for dealing with the changing climate mirrors the evolution of what's going on with engineering, the need to evolve to be able to address the changing impacts of climate extremes on infrastructure. And over the 20-some years, 25 years that we've been promoting and communicating this need to the engineering community and through them to the various decision makers, we've seen really good progress in various countries. So having a webinar like this is a real bonus so that this vision, this need to evolve, does actually evolve globally. Thank you.
Thank you very much. Manuhwa, I saw your hands raised up.
No, thank you very much. I would first of all like to congratulate the presenter for a very, very pertinent subject. And I would like to thank Darrel. I've known him for the past 19 years, and the passion is still, engaging. I would just like to add one or two things. We have, through the vision of the president in the Council of WFEO, started the Engineering Capacity Building for Africa program. And this is a program that deals with engineering plus artificial intelligence. As I was listening through your presentation, I noted that you already have a place on our panel of experts, because we would then want to invite you to look at this code and the impact of technology, especially the fourth industrial revolution, as well as artificial intelligence. We would probably want to move on to the full spectrum of the code, which then will involve adaptation and mitigation, so that we have the full spectrum of the resilience cycle. So David, I know you will not say no. You'll be invited to the CABAP to ensure that we package such an important principle that you have developed over the years. And to the UK team, thank you for organizing this. I want to challenge you now to move to the next stage, where we need as the WFEO to create a toolkit that goes beyond principles and codes. So one to Darrel and David, we would then want to add the mitigation aspect so that we have the full resilience cycle, and also the artificial intelligence and the fourth industrial revolution. And to my friend Davide, the challenge is we need a WFEO toolkit. Thank you very much for the opportunity, Mr. President, and well done.
Thank you.
To us. Yes.
Thank you. Thank you very much. I'm seeing a hand from Nirako Ahmed Donatrian, Biki. With that, you can, yeah. Go ahead.
Okay, you heard me? Hello?
Okay, maybe raise your voice.
Yes.
Raise your voice.
You heard me? Yes. I'm speaking now.
Your voice is too low, and you have you don't want us to have the privilege of seeing your face.
I'm trying to speak. I don't know if you understand me. You heard me?
Okay, from where are you speaking?
From Burkina Faso.
Oh, from Burkina Faso. Okay, that's
yes.
great.
Yes.
Okay,
Yes.
please go ahead.
Okay, thank you. So thank you of the presentator. I'm a member of the Burkina Faso Civil Engineering. I'm a candidate of PhD and working in impact of climate change in the water resource in the Mohun Basin in Burkina Faso. In our country, we consider that sure that the resilience into adaptation is very important. In our country, we consult augmentation of the frequency of the floods, and this situation entering down many risks in the population suffered. And we have not recent rules to calculate the reinforces concrete structure. Actually, donc the recent formula that we use to calculate the reinforced concrete is since 1999, and so the situation can affect it from the conceptions in our country. My question is that to know what would be the contribution of the principles that you are presented to the revision of our standard in Burkina Faso. Thank you.
Thank you. I hope Lapp has had him. Honestly, I was struggling to understand. I mean, to hear him because his voice over here is very low. But if Lapp has had him enough, maybe he can respond appropriately. Or do we maybe take all the comments and questions so that we attend to them at the same time before we close? Any other question or comment?
Do you want me to respond or do you want to wait?
Okay, since there is nobody, I mean, you can respond. You can respond, yeah.
Sure. Well, I guess one thing to look at, flooding situation, and I know the costs of big engineering works are quite expensive. This is one where, your nature-based solutions, look at the feasibility of some of those to accommodate those particular events would be, one avenue to look at. And the other thing I think I would suggest is that you assemble some experts that could advise on, proposing guidance or standards or codes that could, again, it'll take some time, but you could, come up with some rules around, how structures are put in place to make sure that floods are dealt with, or it doesn't cause flooding, because sometimes that happens too, right? So those are the first two things that come to mind from what I'm saying, and that's where engineers, you can't leave it to others. Engineers need to be part of the discussion. So not exclusively so, but certainly be part of those discussions. So I would just make representations to your government that, hey, we want to be involved in such discussions, and we can contribute our expertise and bring in some perhaps some experts on nature-based solutions that might be appropriate for dealing with that situation.
Yeah, thank you very much. Any other comment or question? Okay, Ivan, in the chat, is there any, because there's a link to which people can ask questions.
Well, I would make one comment on that as have to see whether it's how consistent it is with this guideline or this code. And I think as part of our updating of that code, we would want to make sure that we're consistent with that document from a WFEO point of view. So I'll have a look at that and just make sure that we're not sending mixed messages.
Okay, while trying to share the email, may I call on Davide to
Sure.
say something?
Yeah.
I think he was raising his hand.
Correct. I was going to answer to the last question that I guess the last and one before, they were both from Martin, and Martin made the point also about the toolkit and the 50%. Of course, climate adaptation or climate resilience, although they are very different concepts, is one side of the coin of climate change. The other one is the mitigation aspect, and I'm pleased to say that Professor Jianping Hu, who is a member of the working group on climate change and engineering, is developing a toolkit based on the best practice that he is collecting from WFEO members. So that is going to be presented hopefully in Shanghai as a report. And so we are covering that aspect of the climate change mitigation that Martin is referring to in his question.
Okay, thank you.
Just one
Yes,
other
any
thought,
other-
that's David again, just to say, one tool that I did present today that I think could be quite useful is this PI-VC protocol. At least it covers off the risk assessment process to understand your climate risks to infrastructure. And that in itself, learning that tool and how it's applied and could be applied, there's a lot of experience with that protocol, and there's training that's available on that protocol. And I can provide, I'll provide Ivan with a source for that training that you can, it's the Climate Risk Institute that I am associated with. But it's a specific tool to cover a specific part of the climate adaptation suite of tools that is needed.
Okay, that's great. Thank you so much, David. I think we have covered, because the time we have budgeted for this program is actually 1.5 hours, which will cover the introduction and the presentation of the webinar, and then question and answers through comments. And now we have spent like 1 hour 39 minutes, which is 9 minutes above
Mr. President, I think it's worth it. Honest, I'm so happy that the working group and David and Tim took the challenges, and we will meet in Shanghai and launch. Thank you so much.
Exactly. And
thank you so much.
And as you all know, the Shanghai conference will also give all the chairmen of standing technical committees and working groups opportunity to make presentations. And very soon we shall call a meeting with all the STCs. And I think even maybe the notice of the meeting has been sent, I think, or it will be sent very soon. We are going to have a meeting with all the STC chairs and working group chairs, so that within your STC and working group, you can really look for people to make presentations during the General Engineering Congress in Shanghai. And other details of your work will also be showcased during that time. And I know a lot of the STCs and working groups and PICs are doing a lot. And that is why this time around we say we must have opportunity, to all the STCs and working groups to showcase what they have been doing and share it with other engineers globally. So that's what we intend to do in Shanghai, and I believe you will make sure that the people coming to Shanghai will be excited, will feel that they have whatever they have spent in coming to Shanghai has been paid off by the quality presentations we get from the working groups and standing technical committees. So I don't know, the chairman of the working group, if you have anything to add, maybe in closing, you can say. Otherwise, I think it is appropriate time for us to close the webinar. So Davide, you are the chairman of you brought us all here So maybe you have to give the closing remark.
That was just unlucky because the bandwidth went down when you were giving me the opportunity to say a few closing remarks. And I will be very quick. I mean, it's just to thank you, Mustafa, President, and David Lapp for taking the time to go through these code of conduct and the guidelines. And again, really warming each of you following this webinar in considering climate resilience really importantly. And as President Mustafa said in Shanghai, there will be an opportunity to discuss more in details aspects of climate resilience and the climate mitigation toolkit. Thank you.
Okay, thank you very much. Have a good night, good evening, good morning. Thank you. Bye-bye.
Take care, everybody.
Thank you. Thank you all. Thank you. Thank you.